Good morning. We were discussing op amps, and we saw all the characteristics of the single stage op amp, which is a differential pair with a current mirror load. And now, of course, we have already discussed that the gain that you can get from such an op amp is like the gain of a single transistor common source amplifier, right? So to improve that, we can have a similar stage but with a higher output resistance, and that is the cascode stage, or adding a common gate to the common source amplifier and the current sources. Okay, so if we do that, we get a topology which is this one. So now there are of course many more transistors, and if you throw all the components and try to evaluate the expressions, it becomes very complicated. But essentially, each of these combinations this is fixed, right? This can be treated as, for DC, you have GM1, which is the transconductance of the cascode, transconductance of the common source amplifier. Which is the transconductance of the common source amplifier, and whose output resistance has increased, okay, which is approximately GM5, RDS5, RDS1. And of course, we know that we also have these terms when you evaluate the output resistance of only that part, but we don't need to include that, at least to get an approximate picture of what is happening. And of course, for exact answers, there is always simulation. Okay. So now, by and large, it behaves in the same way. So it is best to first understand this combination properly, so that we can neglect all the non-essential parts. And focus on what is important. Okay. I'll call this M1 and M5, but of course it applies to any other combination as well. So the idea is that this is biased at some VGS1, and the incremental signal is applied over there, and this is biased at some VG5, which is a fixed voltage. Okay, so the gate is grounded. So now the DC small signal equivalent, including the output resistances of all the devices, is just that, where we have the increment Vi, the incremental current GM1 Vi, and the output resistance, which is the primary component is okay, and then you have these also. You must have analyzed this many times, so I won't go further into that. But why does this combination increase the output resistance? What is happening intuitively? Okay, so no, that just says your two are in series. Why do you get a boost? So let's look at it. That is correct. Like we know the answers already, right? I'm just trying to look for alternative. Miller effect. Why? From where to where? It is amplified, but okay. So now let's look at these two cases, right? I had only M1 and I have this M1 and M5 combination. Okay. So now here I will apply VGS1, VGS1. So the operating points are the VG5, sorry, not VGS5, VG5. Okay. I will apply an increment to both cases. Now, what is the meaning of output resistance? Let's look at it as output resistance. So it means that if I have some increment here, then some current will flow there. Okay. So if I have some, let's say peak value Vp, what is the current amplitude of the current? Vp times GDS1 or RD, Vp divided by RDS1. Okay. So now what happens in this case? I apply the same signal. What happens here? So you can see that the signal, if you have Vp over there, it is approximately attenuated by Vp times GDS5 by GM5. Okay. So roughly speaking, it's like having RDS5 from there to there and GM5 from there to ground. Okay. So then you will get that some sort of voltage division. So it substantially reduces the voltage swing here. No, because finally this voltage swing times GDS1 is the incremental current, right? So the current has reduced. Essentially, it keeps this constant. Okay. So similarly, if you had, now you can see what happens. This is of course almost impossible in modern processors with low supply voltages, but if you had high supply voltages, you could do that. Okay. You had a triple cascode. By the way, this ratio GDS5 by GM5 is small, very small, only if this is in the saturation region. So both have to be in the saturation region, right? Because if the upper one is in the triode region, then this ratio will not be so small. Okay, if the upper one is the deep triode region, intuitively you can see that it is just a shorting switch and nothing happens. Okay. So now if you have a triple cascode, you can have a large swing here, which becomes smaller, which becomes even smaller. Okay. So finally that current that flows through that. I mean, all this comes out of the analysis also, but it's a good idea. So when you're simulating also, you can look at the signal swings at different parts and see what's happening. Okay. Now, next we'll look at approximately what happens for as a function of S for AC. Now, here what I'll do is I'll just neglect all the RDSs. That is, it means I will set it to infinity. Okay. This is just for simplicity. Okay. So now, what happens for as you sweep the signal frequency, which is the dominant element that appears? So let's say this is terminated in an incremental short circuit. Okay. So as usual, I have VGS1 plus VI over there and VG5. Okay. So now, what is the dominant parasitic that appears? That is here. Okay. What is the value of that parasitic capacitance? Which transistors contribute to that parasitic capacitance? There is M1 and M5. What is it? So you have the drain bulk parasitic of M1. Okay. So CDB1 that appears. And then you have CGS5. Okay. That appears between here and the gate, which is also at ground. You also have CSB5. Okay. So that you can, I mean, just by putting down the transistors, you can guess. So this will have CDB1 plus CGS5 plus CSB5. There will be some parasitic capacitance. Now, what is the effect of this parasitic capacitance? So this is the, we thought of this as a transconductance, right? Without this, it is simply I out by Vi. What will it be without this parasitic capacitance? Without this parasitic, what will be I out by Vi? GM1, that's all. Okay. Now, with this parasitic, what happens? Yeah, at high frequencies. So, what is the impedance looking up that way? 1 by GM5. Okay. So, it will, the current will be split between GM5 and the admittance of this capacitor. Okay. So, what will be I out by Vi? What will be the order of this transfer function? What will be the order of the transfer function? First order. Okay. First order. How many poles, how many zeros? What will be I out by Vi at infinite frequency? 0. Why? All of it flows into the capacitor. Okay. So if all of it flows into the capacitor, then clearly it is 0. So if the gain at infinity is 0 and it is first order, how many poles and how many zeros do we have? One pole, that's it. Okay. And where is the pole? GM5 by that, let me just call this CP, right? It will be at GM5 by CP. Okay. So every cascode node introduces a pole. Okay. So if you have a triple cascode, you will have 2, right? Like you will have a pole because of the parasitic here and another pole because of the parasitic there. Okay. Is that fine? No, depends on the size of the transistors, right? No, it is the total parasitic capacitance from there. I mean, how it is related to the layout, it is something. I mean, how you apportion something to M5 or M1. Okay. So you are talking about that junction is probably shared. May or may not be, but it depends on how you lay it out and so on. But it's basically the total diode parasitic capacitance from there. Okay. If the width of M1 and M5 are different, you cannot share it like that. Okay. They'll be separately laid out and connect. No, not necessarily. Many times what happens is, depends on what you use it for. One of the reasons to use a cascode is also to make the capacitance from here small, from the drain node, because I'll come to the output impedance. So if you want to make this small, the upper transistor could be very small, whereas the lower transistor is large. Okay. And we'll also see that noise and mismatch of M5 do not predominantly come out to the output, whereas that of M1 do. So for matching, if you are making a cascode current mirror, you may make M1 large, but not necessarily M5. There is no, it doesn't really contribute to mismatch anyway. Okay. So they can be, I mean, there are many cases where it has a different size and usually smaller. Okay. Anything else? This part is okay. So every cascode node introduces a pole. So like everything, it comes with a cost. First is the swing limit, the other is these parasitic poles and so on. So now again, if I put the entire op-amp and try to evaluate the transfer function, it becomes very messy. So roughly speaking, you can assume that every cascode node introduces another parasitic pole of the order of that parasitic capacitance divided by GM of the cascode device. Okay. Is that fine? So now what happens to the output impedance at high frequencies? So for calculating the output impedance, both these are incrementally grounded. And we know that at DC, you get that very high cascode impedance. Now, what happens because of this? If you have that parasitic capacitance, what happens? What will be the output impedance at very high frequencies? RDS5, yeah. The output impedance will be RDS5. So you expect that it starts from approximately GM5, RDS5, RDS1 and ends up at RDS5. Okay. So the first order system, so it has to be like that, right? And what is this frequency at which the impedance starts deviating from being the very high value? Which pole? GM5 by CP. Is that correct? Yeah. So is it GM5 by CP? Why is it GM5 by CP? So if I had to, we know the expression for the output impedance at DC. I just had to modify it for AC. What will I modify? That is, I have GM5, RDS5, RDS1. Okay. So I just want like just look at the circuit. Based on that, tell me like how quickly I can modify, how I can quickly modify this for high, including the effect of CP. What should I do? So what has changed? Earlier we had RDS1 here. Now we have RDS1 parallel CP. That's all, right? The impedance between this point and ground is what has changed. Is that correct? Okay. So what happens is instead of this, you will get RDS1 parallel 1 by SCP. Is this clear? So it is this GM5 RDS5 is going to multiply whatever impedance is between this point and ground. Okay. So that is basically now RDS1 parallel with this capacitor. Okay. So where is this pole now? Where is that pole? It is related to RDS1 and CP, not GM5 and CP. Sorry. Okay. And where is the 0? How would you? It is GM5 by CP. This is where the, so you can see how much it is falling vertically. If it is first order, it's the same factor horizontally. These are all log. I won't keep saying that again and again. These are all log plots. Okay. So this kind of thing is also important because like I said, you want to get insights into the problem. Okay. So what happens is that, so in this case and in general, so how are we getting, what was the fundamental mechanism behind getting a higher output resistance? It is negative feedback, right? So this cascode transistor is operating with negative feedback, and that's what gives you higher output resistance. And in general, for any negative feedback system, the loop gain falls with frequency. Okay. So the amount of the factor by which the impedance is boosted falls with frequency. Okay. So you get a very high output resistance, but as you go to high frequencies, you get lower output resistance. Okay. Now this is of course accounting only for that capacitor, and then if you have this one here, Cp prime, what happens to that? Huh? I have another capacitor there. How will you now solve this? Whatever we have already plotted in parallel with 1 by SCP. So we don't know where that will be. Okay. So now, in fact, this plot tells you how you should probably size the transistor. Depending on the size of Cp prime, it could be like that. If it is like that, what will be the parallel combination? If you have two impedances plotted on a log-log scale, okay, and now you want to quickly plot the effect of the parallel combination, what will it be? How will you plot it? Smaller one. And if you want the series, if you want, let's say, two impedances again plotted on a log-log scale, and if you want the series combination, what will you do? Plot the higher one. That's all. Okay. So this is always the case. So if you have R and the impedance of some capacitor. Okay. So if you have R and C in series, it will be like that. If you have R and C in parallel, it will be the lower of the two. Is this clear? And on a log scale, it's reasonably accurate. Of course, around the breakpoints, it will be quite inaccurate, but otherwise, this is a quick approximation. And from that, you can also figure out the values of those breakpoints, right? It's wherever the two impedances become equal. So here, now, Cp could be like that, or it could be, for instance, like that. Which is better? Remember, this whole thing is a current source, right? So which would be better Cp prime to have? The dirty green one or the purple one? Green. Why? Basically, it should have a higher output impedance. So the smaller the capacitance, the higher the output impedance, and that is better. That is also why you would use a smaller device on top. Okay. So sometimes. So now we know what the cascode does in terms of, I mean, at DC as well as you increase the frequencies. Okay. So this again, you please do the derivation yourself and understand what's really going on. Okay. So this Cp will eventually short out this transistor. Okay. So it will reduce the transconductance from the gate to the drain. It will also reduce the output impedance. Now, since I referred to output impedance in negative feedback, so let's say you have an amplifier like this. Okay. With an ideal op-amp, what is the output impedance? 0. So that means if you have an op-amp with infinite loop gain, that will be the output impedance. Okay. Now with a real op-amp, what will happen? So ideal op-amp, the output impedance will be 0. With a real op-amp, what do you expect to happen at very low frequencies? You'll have a very small output resistance because the DC gain will be very large. Okay. And What happens as you increase the frequency? What happens to the output impedance as you increase the frequency? What is happening to the loop gain in general as you go to higher frequencies? It is decreasing. So what happens to the impedance? It will go up. Okay, it will do that. So if you had to represent this by a passive element, okay, this kind of impedance, let's say, I mean, it depends on the phase also that I have not plotted, but let's assume A of S is of the form of, I mean, single pole type, this one. So if you had to represent, if you had to make this type of impedance using passive elements, what combination would you use? R and L, yeah. So negative feedback loop, when you use it to suppress the output impedance, that is when you try to get low output impedance, basically at high frequencies, because of reducing loop gain, it will become higher. So it will look like an inductor. Similarly, if you use negative feedback to increase the output impedance, because of reducing loop gain, it will fall. It will look capacitive. Okay. So the other one here, we wanted very high output impedance, but it becomes lower. Basically, at high frequencies, you get screwed. That's the moral of the story, right? Because the loop gain always falls, and something that should be resistive becomes capacitive, so the impedance drops. Okay. Similarly, here, at high frequencies, it becomes inductive. Okay. Fine. Any questions on this? The behavior of cascode or common source, common gate combination? Now, the next thing is related to noise. Swing limit we already know. I mean, obviously, you have to accommodate 2 transistors. So, that means that you have to leave more headroom, right? You have VDSAT 1 plus VDSAT 5. That is the absolute minimum you have to maintain. And in fact, even for that, you have to make sure that this VG5 is such that this is biased exactly at VDSAT 1. Then you will be able to have VDSAT 5 plus VDSAT 1. Now, if VG5 is such that this is at some voltage much higher than VDSAT 1, then it will be whatever that voltage is plus VDSAT 5. Okay. So, by suboptimal choice of VG5, you can compromise the swing limit further, because finally, what is the minimum drain voltage here? It will be VG5 minus VT of the transistor. So, you first adjust VG5 to be the minimum possible value, which is when you have exactly VDSAT 1 over there. And then after that, you can let the drain fall to the minimum possible value, which is VDSAT 1 plus VDSAT 5. Is this okay? Fine. Maybe I'll just write it up anyway. There are many circuits which you can use to generate this. Again, I won't go into that. But the point is, this VO has to be greater than VG5 minus VT. Now, we want this to be, you want the, this is the lower limit, right? So, you want the lower limit always to be as low as possible. So, choose the minimum possible value for VG5. What is that? Basically, this voltage will be, what is the drain voltage of M1? It will be VG5 minus VGS5 at whatever bias current it is operating at. Okay. And this should be greater than VDSAT1 at a current I0. So, basically, Vg5 has to be greater than VGS5 at a current I0 plus VDSAT1 at a current I0. Okay. Is this okay? So, if you choose Vg5 to be exactly this, you get the best possible swing limit. And now you can think of circuits which will generate that value of Vg5. There are many, we may discuss some of them later. Okay. So, next we look at noise and mismatch, also something I think you have calculated earlier. For this again, I will neglect the output resistances. What I will do is basically this is supposed to act like a transconductor, right? So, I will terminate this with some voltage source and look at the output current that flows. Now, for the incremental picture, this can be considered ground, and then both noise and mismatch can be represented by current sources in parallel with the transistor. Now, what will be the contribution of IN1 if so IN1 will flow through that, okay, because this transistor, I mean there is no, its GM is deactivated, right, and it has no output resistance. So, all of this current has to flow that way. Now, if it does have an output resistance, then this current will get divided between GM5 and GDS1. Okay. So, that division factor you can calculate, but to a first order you can neglect that and assume that all of it simply goes to the output. Now, what about IN5? How would you analyze this? So, the usual thing we can do to break this into two pieces, IN5 and IN5 that way. Now, of course, this bottom IN5 is exactly like IN1, right? So, all of it goes that way. But then IN5 is being drawn out, so it will go there. Okay, so it will just circulate inside the transistor, and I out will be 0 in this case and IN1 in that case. So, to a first order, the amplifier device noise contributes fully to the appears fully at the output current, whereas the cascode device noise does not appear at all. Okay. At least one thing in our favor, we added the device. There are so many penalties to adding a device, but noise and mismatch are not one of them. Okay. So, you can neglect the cascode device to a first order for both noise and mismatch. Okay. Now, we won't have examples like that in our course, but again, why is it that IN5 is going that way? Because the impedance looking down is, here we have considered an infinity, but we also have RDS1 or GDS1, that is also small conductance. But now, if you have a parasitic capacitance, what happens is it does flow through that. Okay, then it can contribute to the noise. So, you have to be careful at high frequencies. Okay, so these things can change. At very low frequencies, this is true that only the cascode device doesn't contribute noise, but at high frequencies, it is possible that it also contributes noise. Okay. And the not all of the current from the main transistor goes out, only a fraction of it goes out. Okay. So, if you are designing very high frequency circuits, depending on the parasitic capacitance, you may see a noise contribution from these. Okay. It's just something to be aware of. That's all. Usually, circuit simulators provide a summary of the dominant noise contributors. So, from that you can see Now, you shouldn't be surprised if you see that the cascode device is also contributing noise, then you have to look at why it is contributing noise. It is possible because we make so many approximations here, some of them may be violated in that case. Okay. Any questions? So now, one question I have is, we just concluded that if you have a current source here, let's say the noise current, right? It doesn't appear. But what changes in the circuit? Will it not have any change? Will nothing change? What is it that actually changes here? Huh? Why? No, no. The output resistance cannot change because of adding a source, right? The output resistance is computed without any sources. No, I mean, is it? Does it look likely that I add a current source to the circuit and nothing changes in the circuit? What is it that is changing actually? Right. So what happens is that this is circulating internally. So all that IN5 does is it produces a voltage IN5 by GM at the cascode. Okay. And that's all that happens. Now you can see, if we assume zero output conductance for this, even if this voltage is changing, that will not cause any change in current. But of course, if this output conductance is not zero or you have parasitic capacitance, this wiggle will produce some current which will appear at the output. Okay. So generally, it's also useful to have multiple ways of thinking. I mean, that is, you get something from small signal analysis, then you can also look at it in a sort of large signal way to see what's happening. And so. Any questions? So that basically tells us all we need to know about cascode op amps, right? And with that, we can sort of write down the data sheet of this. And we have a number of these additional nodes. So let's say drain of M1, drain of M2, drain of M3, drain of M4, and then gate of M3. Okay. So to first order, the transconductance is what of this op amp GM1. And the output resistance, what is it? We can do the same thing as earlier. We can take the parallel combination of this down up branch below that and the branch above that. Okay. So this is approximately GM5 RDS5, RDS1, parallel, GM7, RDS7, RDS3. Okay. And then of course, the DC gain will be the product of these. Okay. Now, the unity gain frequency with a load CL, what will it be? Unity gain frequency of the op amp with a load CL. JM1 by CL is the same as earlier. What will be the slew rate? What is the slew rate? It is the maximum rate of change of the output. What will be the slew rate? Yeah. So the maximum current that can be pushed to the output is 2I0 in both directions. So it will be 2I0 by CL. So these parts are largely the same as before. Okay. What is the input referred noise based on all the discussions we had? What will it be? How is it related to the input referred noise of the simple op amp? Same, because the cascodes don't contribute any noise, it will be the same. And how much was it? We had 16 by 3 kT by GM1 just because of the input devices, and the load devices had that one. Okay. Similarly, the input referred offset variance, what is that? How is it related to the offset variance of the simple single stage op amp? Same. So what was the expression? 2 times sigma VT1 square plus sigma beta 1 square times I0 by GM1 square, right? Plus sigma VT3 square times what? GM3 by GM1 square plus sigma beta 3 square times, what is it? I0 by GM1 square. Okay. Please verify this, but basically that's what it is. So these things are basically the same, no change, right? Now, one important change is that you will have many more parasitic poles. Earlier, how many did we have? In I out by V in, if you think of this as a transconductor, in the simple single stage op amp, how many parasitic poles did we have? How many parasitic poles did we have? Extra poles. Now, if you think of only I out by Vd, right? Not V out by Vd, I out by Vd. How many parasitic poles did we have? 1. That is because of this gate of M3. In fact, that created a 0 pole, this thing, right? You get half the current at high frequencies and so on. Okay. So now how many parasitic poles will you have? What do you expect? How many parasitic poles will you have? Six. Why 6? Not 3 on each side. There are 5 extra nodes, right? D1, D2, D3, D4, and G3. Okay, so expect 5 poles. Now it could be that the poles at D1 and D2 are identical, right? Because they have the same parasitics and so on, but you get many more extra poles. And actually, this part is complicated because there is some parasitic pole and there is also a feedback loop around it. So this can has its own behavior, right? It's not just like of the form GM by something. It has its own parasitic capacitance. So that can move this feedback loop will move the poles within this loop and so on. So, but we won't worry too much about it. I'll just say that you will have okay. So at D1, what is the conductance component that you get for the parasitic pole? At D1. I mean, these poles will be of the form of some conductance by some capacitance. What will be the conductance? GM5, right. So this will be GM5, this is GM6, which is the same as GM5. What is the capacitance you get at this point? You have CDB of M1, CSB of M5, CGS of M5, okay. So you have and here it is the same thing, right. So these two actually provide the same pole for two halves of the current. So eventually you will have only one pole because of that. Okay. Anyway, these are sort of details that we normally don't work by hand, but we need to know this so that when you get the simulation result, you can understand them. Okay. And then this D3, D4, this will be GM7, GM8, which is the same as GM7. And these are again similar. It will be CDB3 plus CGS7 plus CSB7, and this is the same. And at G3, what will be the parasitic capacitance? Which transistors contribute to parasitics at G3? M3, M4, M5, M7. Okay. And what will be the conductance associated with this? Let's say G3, only G3 had a parasitic capacitance. There are no other parasitic capacitances. Okay. And that parasitic capacitance is contributed by all these transistors. Let's call it CP. Where will be the pole? What is the conductance associated with that? What is the conductance? 1 by? Why? What was the conductance there when we didn't have a cascode in the simple case? 1 by GM3. GM3 is the conductance. What will it be now? GM? Why? What is the small signal conductance looking up? GM3. Conductance is GM3. Why? If you apply some test voltage, GM3 times test voltage is drawn there. So this is GM3. Now you have M3 with some cascode device and you have that. So what is the conductance? If you apply a test voltage, how much current is drawn? It is still GM3 times that, right? So the conductance here is still GM3. So this is still GM3. Only thing is this will be 2 times CGS3 because you have CGS3 plus CGS4 plus CDB5 plus CDB7. Okay. This is likely to be the lowest frequency pole because it has many transistors connected. But anyway, these things, I mean, you can kind of recognize that there are many poles, and also these two, or rather not these two, the one at the drain of M3 and G3 are also in a local feedback loop. Okay. So that is basically it about this type of cascode op-amp. We will discuss another type where here for the NMOS differential pair we used NMOS transistors as common gate, but that's not necessary. We can use PMOS common gate for NMOS. Similarly, here for PMOS current mirror we use PMOS cascode, and that can also be inverted if required. Okay. So we will discuss the other type of cascode, right? Okay.